Good morning. My name is Michael Busch. I work for Twitter. I'm the tech lead of the search infrastructure team. I work in San Francisco in the HQ of Twitter. And today I would like to talk to you about how we do real-time search. And to start off, I want to show you some numbers. We currently index 230 million tweets per day. I think it's actually 250 already, but yeah, it's growing really fast. We have about 2 billion queries per day. That's roughly on average 23,000 QPS, queries per second. Those are not all user-entered queries. Those are also queries that come from third-party apps or iPhone client and that kind of stuff, so API traffic. We have an indexing latency of way less than 10 seconds. That means after you tweet it doesn't take more than 10 seconds until a tweet becomes searchable. And the average query response time of all these queries is about 50 milliseconds on the back end. So these are pretty crazy numbers. That's why we had to change entirely the approach how we do real-time search at Twitter. And I want to give you a little bit of history in the introduction, how Twitter search started and what we changed. But not too long, then I want to give you a quick overview of the entire search architecture at Twitter. But then I want to dive deeply into our inverted index. I want to explain a little bit what an inverted index is to get everybody on the same page. And I want to explain what changes we made to Lucene to support real-time search. And then to describe that, I'm going to cover our memory model and our concurrency model, which is, I think, the most interesting piece of this component. And if you have time at the end, I guess we start a little later now. Let's see if you have time at the end. I'm going to cover top tweets, which is a feature we have. If you search on Twitter, usually you get the tweets ranked in time order, but often you get one top tweet on the very top, which is a tweet is a very relevant tweet. Maybe it got a lot of engagement or from very popular users or that kind of a combination of those. So that's a different challenge because then you have to not only do then you don't only have real-time search, but you also have real-time relevant search, which is another challenge. All right, let's get started. So in 2008, Twitter was really small still, and they acquired a small company called Surmise. Surmise had only, I think, like a handful of people, like 6 people or so, and they did the first version of Twitter search, which was interestingly based on MySQL. And so it didn't even have an inverted index like Lucene. It was all the words were decomposed into MySQL tables. And surprisingly, we scaled that until mid of last year, until we had 800 tweets per second, and I don't remember how much QPS we had. But it was a pretty big challenge to scale a MySQL-based search system to those numbers. And it was clear at that point it wouldn't scale very much longer. So that's why we decided beginning of or mid of last year to rewrite the entire engine in Lucene. It's based now on Lucene. It's heavily modified, as I'm going to show you. The whole inverted index data structures are basically changed. But we still use actually an unmodified Lucene jar. All the changes we made are on top of it. And we write on trunk of like 2 months ago or so. We frequently haven't updated in like 2 or 3 months. And we basically use the entire search layer unmodified of Lucene, like the Boolean queries and all that kind of stuff, unmodified. But under there, the low-level inverted index APIs we implemented. We implemented the same APIs so that we can use the other stuff unmodified. So we have the architecture consists of different main components. The first thing we have is an ingester, not a very surprising name. It consumes the firehose, all the tweets, and pre-processes the tweets for indexing. So what it does is tokenization, normalization. It expands URLs. It looks up geocodes. So URL expansion, with that I mean if you have a bit.ly link or so, it tries to resolve the full URL and follows redirects and that kind of stuff. And then the ingester puts those pre-processed tweets it converts it into a serialized thrift format. Do you guys know what thrift is? Who doesn't know what thrift is? Okay, so think about thrift as an alternative to Java serialization, with the benefit that it actually works across languages. So you can basically define in a Thrift definition language, very simple language, like stuff like structs or enums. And then you have a compiler that generates bindings for different languages, for example, for Java or for C or for Ruby. And then you can communicate using that serialization format across those programming languages. So for example, if we had a Ruby client, that Ruby client could serialize a search request into Thrift, send it to the Java backend, and the Java backend just uses it by Thrift-generated Java code to deserialize all the fields. So it's kind of nice because it also supports backwards compatibility. It's kind of like Avro, if you know Avro from Hadoop. It's very similar to that. Thrift was started a while ago by Facebook and open source. So here we actually still have MySQL left, but currently we're also working on replacing it entirely. But the reason we still have it here is for replication across machines. So we basically write, the ingester writes a serialized Thrift tweets into a MySQL database, a master table, and then we use MySQL replication to fan that data out to a lot of machines, where then the Lucene index runs on. By the way, the name earlybird is our internal name for the Lucene engine. Twitter always uses bird names for everything. So the earlybirds are the ones that run on the JVM and run the modified Lucene. And they build a in-memory inverted index, so it's all in memory. And they do that by tailing the MySQL slave databases. So if there's a new tweet added to the master table by the ingester, the earlybirds, by tailing the database, get it and index it into memory. It's pretty simple. So we have another component called the blender. That's more on the search side. The other ingester and MySQL was on the ingestion side. Blender's on the search side. So Blender's a Thrift aggregation service. That means, for example, the front end gets a search request and sends it to a Blender machine. So there's also load balancer before. There's, of course, multiple Blenders. Everything is like, times X here, all these boxes. But so let's say a Blender gets a search request as a Thrift from the front end. So now, of course, not a single earlybird machine contains all tweets on the entire index. So it's of course, sharded, right? So the Blender figures out a covering set of earlybird machines that it has to send a request to get all the search results back. So the Blender splits up the request and sends it to all those earlybirds and waits for responses. Blender is completely asynchronous, so there's nothing blocking going on. So it's sending all those Thrift requests to the different earlybirds and waiting for the responses, and then it merges the responses. So for example, it could do just a merge sort or something. To get really the top 10 results or the latest 10 results. And then it sends those 10 results back to the requester, to the front end, or to the API. It does more, the Blender does more stuff. The Blender is kind of cool. It can handle dependencies on multiple different services. So for example, if you search for Lucene near San Francisco, it has to translate near San Francisco into geocodes. So then the Blender would detect, oh, I have to call the geo service first. It calls the geo service, waits for the response, and then it can call the earlybirds. And it maintains a DAG, a graph, and figures out what the dependencies are of the different services, and calls them with maximum parallelism, but also in the order it has to call it to resolve the dependencies. So that's a very quick overview of our architecture. Now I want to dive into earlybird. And to get everybody, as I said, on the same page, let me talk a little bit about what an inverted index is. Let's assume we have these 6 documents here. And we want to search in them, right? So what we do to build up an inverted index, and that's standard Lucene. That's nothing special in Twitter. We tokenize and lowercase all these documents and find out all unique terms that occurred in all of the documents. So you can see that here in the big table, the dictionary, which is, in this case, a sorted list of all unique words that occurred there. You see another column that's frequency. That just says how often and how many documents did each word occur. And then you have, on the right side here, you have something that's called a posting list. Again, that's standard information retrieval, not even special to Lucene or earlybird. And the posting list is just a linked list, basically, that contains the IDs of the documents that contain the word. So for example, if you want to search for the word keeper in those 6 documents, what we do is in the dictionary, we find the word keeper and look up the posting list. And then we see, OK, it occurs in documents 1, 4, and 5. And if you see there on top, if you look there, then you see that's really what the documents are. So it's really quick. You don't have to scan, of course, the documents, but that's why it's called an inverted index, because you invert the problem, right? You can look up by term. Let's look a little bit into how posting lists are encoded. If you looked at the previous slide, you can probably guess that the majority of data we have to store in an inverted index is most of the storage is occupied by the posting lists, right? These are really big lists always. So we have to efficiently encode them. So let's say we have those 6 numbers to encode up there. What a common technique is, for example, in standard Lucene, is to use delta encoding. So you actually compute the difference of the doc ID and the previous doc ID. So for example, 9000, 9002, the difference is just 2. So you made the number much smaller. You don't now have to store 9002 anymore, but 2. So now if you just put it into a 32-bit integer, it doesn't matter because you always need 4 bytes. But if you combine this with a compression technique, for example, VINT encoding, you can benefit from having smaller numbers. The VINT encoding is the standard compression technique in Lucene. Now, in the next release, you will be able to choose from different ones with flexible indexing. I think there's another talk today about that. But for years and even currently, the default compression technique is VINT. And how it works is it actually uses only 7 bits of a byte to encode the value itself. And the most significant bit has a special meaning. And that bit indicates if the following byte is still part of the same value. So in this case, if you want to encode number 5, that fits into 7 bits. So the first bit is 0, which means this is the entire value of the current number is stored in that byte, right? But if you, for example, want to encode the 8985, that doesn't fit into 7 bits. The first bit indicates, OK, you have to also decode the next byte to calculate the current value, right? So now you can use 14 bits by using 2 bytes. Of course, in the worst case, if you have really large numbers that are bigger than 2 to the power of 28, I guess, then you actually need 5 bytes. But those big numbers are very uncommon, actually, in inverted indexes. Because usually you don't put like hundreds of millions of terms into a single index. And then also, you would have to have in the same posting list gaps that are so big, which is not very common. One problem here that Lucene doesn't have, but what we had in early bird was that because these values occupy a variable number of bytes, we cannot write them in Java atomically, which means you can an integer or long, any primitive type in Java, you can write atomically, right? But you cannot write 3 bytes in an atomic way, which can cause problems for concurrency, as I'm going to show you later. So we wanted, in Twitter, we wanted to be able, for our concurrency model to work, we wanted to use primitive types that you can read and write atomically to and from. The other problem is, if you think about the delta encoding, you can only read it in this direction, to the right, from old to new, because always a posting depends on the previous one. So, but if you think about the problem real-time search, you append at the end, of course. You write the posting list from old to new. There's no other way to do it. But it would be much better to search backwards, because usually you want to show the most recent results if you search. So it would be really wasteful to every single time if you execute a query to start from the beginning and read all the way back just to get the last 10 results. That would be really inefficient. So we wanted to also be able to read the other direction. Yeah. So these are our problems we had with VINT. It's just summarized on the slide here. So that's why we use a different encoding in Twitter. And it's not really actually that sophisticated. It's very simple. Every posting in Twitter is mapped to a 32-bit integer in this way. So we use 24 bits for the doc ID. And the doc ID is not a delta, it's an absolute number. We use 8 bits for the text position. That I haven't mentioned before. Usually what you also do in an inverted index, you don't only store the doc ID, you also store where in the document a word occurred. You need that for phrase queries, for example. If you want to answer the query New York, you don't only want to find out New and York occurred in the same document, you also want to check if they occurred next to each other. So for that, you need to store positions. So now if you think about tweets only have maximum 140 characters. So with 8 bits, you can encode 255 possible positions, so that's enough for us, right? That's why 8 bits are enough. So we have 24 bits left, and that is a maximum of 16.7 million doc IDs. And that's why also the maximum segment size for us is 16.7 million. So on each early bird, we have multiple segments. I don't know how many right now, but each segment at max has 16 million tweets. And then when we execute a search, we go through all of those segments to find all the search results. So the decoding speed of this is super fast, much faster than VINT encoding and delta, because now the only thing you need to do to decode those two values is for the doc ID, you need to do 1 bit shift, 8 bits down. And for the text position, you have to do 1 bit mask, that's it, which is the most efficient operation you can do. This is not really simple, right? You can now read in both directions. Without delta encoding, you don't have dependencies on across different postings anymore. So we can start reading here, and if we only need to find 3 results, then after we found 3, we can terminate and don't have to process the rest of the posting list anymore. So actually, really, if you just have a single term query, if you just search for a hashtag, for example, by default, I guess you get 10 or 20 results. We really only have to read 20 integers, that's it. So to summarize, ints can be written atomically. In a second, you will see why that's important to us. Backwards direction works. Every posting point is a possible entry point for a searcher. That means I can anywhere in the posting list start and read backwards or forward, which is also going to be important, as I'm going to show you. We can skip without needing additional data structures because you have a fixed format. You always know where posting starts. So you could skip to a particular one and check if I can skip my iterator there, which is not possible if you have compressed posting lists because you never know where the different postings start. You may skip somewhere in the middle of a multiple byte VINT. Yeah, so we need about, of course, the downside is we need about 30% more storage compared to delta encoding and VINTs. But what we do is, I mentioned already the multiple segments. So there's only 1 segment on each box where we actually append to. And when we reach the boundary of 16 million, that segment is full. So at that point, we will never append to that one again. We may delete tweets from that, but we'll never append documents to it. So at that point, actually, what we do is we go through an optimization step and compress posting list after the fact. And I'm not going to cover that because it's requires too much time to talk about it. But so only for the latest segment on each early bird, we actually need 30% more storage. After that, they're actually even more efficient than the delta encoding is. Any questions so far? The question was, when we do the compression, is it still bidirectional? It's only one direction, but in the new to old direction. So in the direction we always search. Yeah. So kind of we turn them around and compress them. Yeah. Or if the same term appears twice in a tweet, yeah, we actually for that we store 2 4-byte postings basically. We repeat the doc ID, but the 30% more storage that includes that wasted space as well. Okay, cool. So now how do we store all that stuff in memory, right? We have basically the 2 main components that I mentioned already. We have a dictionary and we have the posting list storage. We don't know yet how it looks like. Let's talk a little bit about the dictionary. So this is a dictionary, and I said already we have to, per unique term, store some additional metadata. For example, the frequency or pointers to posting lists and that kind of stuff. So at Twitter, we don't support right now wildcard queries. If you want to support wildcard queries, you need a sorted dictionary. Since we can just live with the hash table. The hash table is very simple. It's an integer array here on the left side. And let's say we find the first term in the segment, and the term is then hashed into some position. So we compute the hash code of the term. Maybe it hashes into the slot. And then we assign the first term a term ID. The first term gets ID 0. So we write the ID 0 into the hash table. That ID is also then an entry point into these arrays, which we call the parallel arrays. They are called like that in Lucene, because they look parallel, I guess. And for each metadata that we want to store with a term, we have its own array. So for example, for the frequency, which was the second column on the previous slide, we have an integer array. And the frequency for the term with ID 0 goes into the first slot up there. If we index the second term, it hashes somewhere up there, but it gets ID 1. So it's written in the second row here in these arrays. So the cool thing about this is, of course, the hash table has to be oversized. It maintains a load factor of like 50%. So even in the best case, it will waste 50% space. But these arrays here, they can always be very compact because they are not sparsely filled, they're densely filled, right? So we don't have to oversize them very much when we grow them. And another data structure here is a storage for all the UTF-8 characters. We have also a pointer in those parallel arrays that points to to the offset in this big character pool here where the term starts. We need to store the terms itself. That's also how Lucene does it, very similar. Because you can get hash collisions on the hash table, so to resolve those collisions, we need to keep the original text here. Yeah, one thing I want to point out is this is actually how Lucene looks internally now, roughly. Also with these parallel arrays. We made the change like half a year ago, or maybe a year ago or so. Before, for each term, we had its own object. And when we switched to this model, where actually the number of Java objects that we have here is independent of the number of terms. As you can see, we have I think we have in total 6 arrays or something. So we have much fewer objects than we actually have terms. And that helped garbage collection significantly. Because before, if we had 1 million terms, or we have, I think in early bird, we have about 10 million unique terms or 20 million unique terms per 60 million segment. So you would have 20 million objects, and they would all be long-living objects, which is really bad in Java, almost no matter which garbage collector you use. That makes the garbage collection very expensive. So we by avoiding having so many objects, we improve performance it depends on how much heap size you have, but I saw improvements up to 400%. If you run with a very full heap, on an average, indexing Wikipedia documents with Lucene, it was like 80%, 90% improvement. Yeah, garbage collection is something you really have to think about if you design an in-memory index as well. So the best technique is usually keeping a very low number of objects and also not allocating too big. Cool, so that's how the dictionary looks like. We have the dictionary, we have the parallel arrays, and now we have to think about the posting list storage. Let's think about what problem we have here. So the problem is we need to store a huge number of lists, as I said earlier, 20 million per segment. And the first time we see a new term, like it could be a new hashtag, for example, that we haven't seen before, we have no idea how often we are going to see it. So it could be that this is a single unique term, we will never see it again. It could also be this is a new hashtag trend, and we're going to see it 1 million times in the next hour. So this is a complicated problem. We don't know how much space to allocate the first time we see a new term. Again, we want to limit the number of Java objects, keep them independent of the number of terms and documents. And yeah, the other 2 points I already talked about. One thing I want to point out is we want this index to work in a log-free way, which means we never have to use synchronized keywords mutex logs because that would be a nightmare for such a concurrent system. And in the next section of the talk, I'm going to explain how the log-free stuff works. So I'm going to now explain the data structure where we store all the posting lists. So we have 4, which we call pools. And each pool is basically a gigantic integer array. Right. It's going to make sense in a second. Bear with me. Under the covers, you don't really have to remember that too much, but just under the covers, each pool consists of 32K integer array blocks. They always have the same size. And if we want to grow, we just allocate a new block and append it to the pool. So you can forget about that, really. But just remember that we have 4 pools, which are 4 integer arrays, and each of them we can basically grow infinitely, independent of each other. The only reason why I wanted to point out these blocks is this is very garbage collection friendly as well, because again you have rather low amount of objects, and they always have the same size, so you actually don't fragment your heap. So on each pool we have a fixed slice size. A slice is a portion of memory you can allocate on each pool. So the lowest one has a slice size of 2 to the power of 1. The biggest one has a size of 2048. On each pool, you can allocate multiple slices and address multiple slices. So now, why do we do this? So so remember, these are integer arrays, and as I have shown you earlier, an early bird posting fits into one integer, right? So that means if we basically have a slice of size 2, it means we can store 2 postings in there, actually, and that's what we do. So the first time we see a term, we say, okay, we don't know how often we're going to see it, so we just allocate a slice of size 2 for it, and now we have room for 2 postings. Since we have already seen it the first time, we stick the first posting in there, and we will have room for one more occurrence of that same term. Let's say we see it more than 2 times. Then we allocate a new slice, but we go up a level. Because now we say, okay, it's likely if we see it already the 3rd time that we're even going to see it more often. So then we allocate another slice of size 16. So now we have 18 possible slots for term occurrences of that term. If we see it even more often, we go another level higher to, and then we have 128. And then we go to the 2048 pool. Let's say, so if we filled up the green box on the top, it means that we have seen the term roughly, I guess, 2,300 times or so. So if you see it even more often than that, if it's a really popular term, it could be also a stop word or a trend. Then we just stay on the highest pool and allocate more slices on that level. We don't go higher anymore or change the slice sizes at that point. Just a reminder, as I said, this is how our posting list format looks like, or posting format looks like. We always map it to an integer, so we can save these into those slices. Now we also need to be able to address any posting in this big data structure, right? So it's very convenient if you can actually store a pointer to any of those slices also in an integer. As the reason is going to become clear in a second. So that was the goal, to actually fit an address to a posting into an integer itself. So the way it works is we use the 2 upper bits of the integer for the pool index. Remember, we have 4 pools, so 2 bits are enough to encode the number 0 to 3. Depending on in which pool we are, which pool we address, the slice size is fixed, right? So if you're on the highest pool, if the first 2 bits indicate number 3, we know we are in the highest pool, and then we know the slice size is 2048. That means we need 11 bits to point to a certain offset within a slice. Yeah? If you're on the lowest pool, we only need 1 bit to say it's first or second integer in that slice of size 2. So depending on which pool we are in, if you need 11 or 1 bit, we have in the integer here 19 to 29 bits left, right? So we use those bits to actually point at which slice in a pool we are talking about, right? Because you have, with this you point to an offset within a slice, but with the middle section you have to point at a certain slice ID within the big pool. So the red arrows are the pointers basically. And now I want to show you how an entire search works. So if you go to twitter.com, enter a search term, hashtag Lucene or whatever, we look it up in the dictionary, find the hash position, find the term ID, look up the term ID in the parallel arrays, and then we have some column here for a pointer into the posting list pool. This one is encoded like I showed you on the previous slide. So it has 2 bits for the pool and 11 bits or so for the slice index. So we can decode the position within the pool. And then so it points to somewhere. And that's where we start searching backwards, right? That's where we traverse the posting list backwards. And then maybe we reach the end there of the posting list here, right? So I'm going to try this now. Right, so we get here, right? And then we search backwards here. And we haven't found enough results yet. So what we need to do now is we need to find the previous slice of the same posting list. So we use this pointer. Always the first integer in a slice is actually a pointer. It's not a posting. So if we reach the first one, we know, OK, decode the pointer, go to the previous slice. Now what we do, we keep searching until we find the end. We couldn't early terminate yet because we didn't find enough results yet. So we know, OK, this is a pointer again, which points to the lower slice. So search this one, follow the next pointer, this one, and go to the very end. And then maybe we found enough results. Maybe we even early terminated somewhere earlier, or we say we couldn't find any results. That's basically how it works. If there are no questions, I'm going to continue with the concurrency model and how all this stuff works in a log-free way. OK, so a few definitions about concurrency first. I guess everybody knows what pessimistic locking is. Pessimistic locking is just, basically in Java going into a synchronized block, which means that there's only one thread that may access that block at the same time. You use that technique if you expect that conflicts on that resource that you're trying to protect are very likely, because retry logics would not make too much sense there. If you know, okay, there's going to be a lot of contention there, it makes sense to use synchronized blocks. But there's a different technique called optimistic locking. It's not used as frequently as pessimistic locking. It's a little bit harder to design algorithms using that. But basically, the idea is that you try an operation and you can, without locking, and you can actually detect if it succeeded or failed. And if it failed, you retry it until it succeeded. That's why it's a good technique if conflicts on that resource are not very likely. They can happen, so you have to make it thread safe. But it's not going to happen like all the time. So in most cases, you don't need to run the retry logic. If you had a lot of contention, it wouldn't make sense because all the threads would be spinning in retry logic all the time. Okay, a few more definitions. A non-blocking algorithm is basically just an algorithm that doesn't deadlock. A lock-free algorithm is an algorithm that is where there's guaranteed system-wide progress. So there's always a thread, at least, that can execute some business logic. A wait-free algorithm is another step beyond that, which means in a wait-free system, every thread can always make progress. There's no thread that ever waits for getting a mutex lock, entering a synchronized block, for example. So wait-free is the best thing you can do. It's also the hardest. But we wanted to try to design this in a wait-free way. We changed recently Lucene to the concurrency model in Lucene. That patch got committed. It's going to be released as 4.0 to now have a single writer thread and multiple reader threads. And that's also what we need for making the real-time search working here. There's only one single thread that always appends to those data structures that I've shown previously, to the posting storage and hash table and stuff. So we don't have to worry about multiple threads corrupting the same data structure. But we do have to worry about readers seeing a consistent snapshot of that index. Yeah. And in Java, and this sounds weird to some people who haven't thought about this very much, it's not guaranteed that the one thread sees updates a different thread made, unless you take care. You explicitly make the other thread see them. There's a really good book about that I always want to recommend. It's from Brian Goetz, Java Concurrency in Practice. I highly recommend reading it if you haven't. It's an awesome book. And from that book, I took some examples, some rules, how you can easily describe the Java memory model. And it sounds a little scary, but it's not. It's really simple, actually. So I took only a subset of the rules to describe it. The ones we need to describe our wait-free algorithm. So 3 rules here. The first one is called the program order rule, and that's a rule everybody who has ever programmed knows. It basically just means, so I'm going to read it, each action in a thread happens before every action in that thread that comes later in the program order. It just means the program is executed in the order you write it. Line 1 is executed before line 2, if you only look at one single thread. So everybody knows that rule. Then there's the volatile variable rule. And that says a write to a volatile field happens before every subsequent read of that same field. That sounds a little weird because it kind of has 2 concepts of time in the same sentence. So this is how I think about it. So if you have 2 threads, right? One thread writes to a volatile field, and then in absolute time, like a second later, a different thread reads from the same field. It's guaranteed that that thread sees the update the other one made before, if that's a volatile field. That's what is meant with happens before and subsequent. Subsequent is kind of meant like absolute time. It really happens in absolute time later that the other thread tries to read that volatile field. And then we have transitivity. If A happens before B and B happens before C, A happens before C. Okay, so let's look at an example. Let's say we have one field X, it's an integer, it's not volatile. And thread 1 assigns a value 5 to field X. Because it's not volatile, what it can actually do for performance reasons is it can put that number into its local cache. It doesn't have to write it actually into the RAM. It can just write it into L1 cache or whatever. So the RAM version of X just still has a value 0 because there's nothing in the program that forces the value to be written into the cache. From cache into the RAM. Now let's say we have a different thread, and that thread reads x and loops forever until x becomes 5. You know, if you look at that program, you would think that should terminate. But likely this will never finish, this program, because there's nothing in this program that forces 5 to be written to the RAM. And thread 2 doesn't have access to the private cache that thread 1 uses to write the 5. But now let's say we have another field, B, and that's volatile. And let's say now thread 1 does the same assignment, x equals 5 first, but then it assigns the value 1 to B. And because it's volatile, it actually has to write it through to the RAM. So there's not going to be a different copy in its cache. And now let's say thread 2 reads, does a read to B first. And it's going to see the correct value for B, again, because it's in the RAM. And then it has the same loop. So now let's analyze that program with the rules we just learned. Let's take the program order rule. If you just look at thread 1, x equals 5 happens before b equals 1. That's the order we have written the program in. Same here. The dummy read of b happens before the while loop. Now, and by the way, the y-axis is time here in this direction. So now let's look at the volatile rule. The write to b equals 1 happens before the dummy read here. So we also have a happens before relationship there. And now with transitivity, we can actually now say that x equals 5 happens before the loop, which means now we guarantee that the loop will actually terminate, even though we didn't actually make the field x volatile. And that's pretty awesome, because now we can consider that field B as a memory barrier, which we can use to actually flush other data structures the first thread, for example, used to the RAM. So this all sounds like weird to have an example about it, because otherwise people don't trust me. You cannot see, oh, you can see my mouse, cool. Okay, so first thing here we have is we have a counter variable. Here this is not volatile, right? And we have a maximum constant value of 1,000. And we have a very simple writer thread here, down here. It's in the main method. All it does is it increments the counter until it reaches a max of 1,000. So it does 1,000 times plus 1. And after that is done, it sets the other field, memory barrier, which is, if you look up here, it's a volatile field, right? It sets that 1 to 1. So it makes it right. So this is basically the same as field B here before, right? The B equals 1 call. So it does a bunch of writes to fields to a field that is not volatile, 1,000 operations that are not volatile, and a single operation that's volatile here. So then it starts 10 reader threads here, right? And the reader threads are extremely simple as well. They're basically the second thread on my slide with a loop that forever spins and basically waits until that counter reaches the maximum value. And when that's done, the loop terminates and prints out, OK, I'm done. So let's run the program. And this one is commented out this line. So it actually right now doesn't read from the volatile field. So let's run this program. You can see it printed out, OK, all the threads started. But it's still running here. Yeah, it's I could terminate it now. And no reader thread actually said I'm done, which means this is still running. I mean, we could wait now for a while, but I guess by now it should have counted to 1,000. So unless nobody believes it, I will terminate it now. Okay, I terminate it now. Okay, cool. So now I will uncomment this line. And I actually don't really do anything meaningful here, right? The only thing I do is I read from a memory barrier and put it into a dummy field. And even Eclipse here says, gives me a warning that this dummy is never used. So Eclipse recommends to remove this line. Right? So now let's start this one. And now we are done, right? All the threads are done here. And here you can see the program terminated. And this is really cool because, again, I made 1,000 writes in a non-volatile way, as efficient as you can do it in Java. and delayed my flushing of the cache to the RAM until I really wanted to, until I set the memory barrier to 1. So I can basically, with this simple program, control in Java when I flush the cache stuff into RAM, which is cool. No, it's a good question. The question was, do I really control it, or do I, you said limited? I would say I force it at that point. It's like I compare it often to an fsync. And then if you explicitly call fsync on your file system, you make sure that the file system buffer is synchronized to disk, right? But it can happen before, and actually that's kind of the reason why we try to delay it, because sometimes you may get that for free. Because your CPU, your operating system, or the JVM, they run all sorts of operations, right? And maybe sometimes it does it for free for you because it was writing like a block in the same region anyway, so maybe it's flushing for you, right? If you would actually every single time write to the volatile field, it would be very, very slower. Even though of course you transfer the same amount of data from cache into RAM, but you do it much more often, and the overhead of doing it 1,000 times, versus like the whole block a single time later is significant. So now how would you use that for our engine? It's very simple actually. You can think of an early bit, we have one volatile field, which is called maxDoc, and that stores the ID of the latest document we indexed. So for example, the index writer could now write 100 documents, and all those writes, everything it has to do is non-volatile, it's as efficient as possible. And then it does this one write to maxDoc, which kind of is a volatile write and flushes everything from the cache into RAM, or makes sure it's flushed. And the index readers, for every of our 23,000 queries per second, we actually open a new index reader, because for us it's extremely cheap. Because the only thing now the index reader has to do is, before it executes a query, it actually reads the maxDoc, and because it's doing this volatile read, it's making sure it's crossing the same memory barrier and sees everything that index writer wrote before it updated the maxDoc. So if the maxDoc in this case is set to 100, index reader knows, okay, I'm definitely allowed to read everything before document 100. Yeah, so the same picture, because maxDoc is volatile, we have the same happens before relationship between write and read the docs here. So to summarize, we don't have any exclusive locks, any synchronized blocks in our code. The writer thread can always make progress. There's only one single writer thread. Since there's no exclusive lock, it can always append to it. There's nothing it would prevent it from that. We have in one place actually an optimistic lock, but that optimistic lock is extremely simple, and it doesn't really have a retry logic that is a loop. It basically only has two possible things it can try. Usually the first one succeeds. If it fails, it knows it immediately, and then at that point knows the second attempt will succeed. It would take really long to describe it. I spent with one person 8 hours in front of a whiteboard to talk about this problem, but it works. It's running for a year in production, so it works. And it's guaranteed to always make progress because it only has those two possible cases it could execute. So far, we only have talked about the invert index and scoring in real-time modes and recency mode, basically. But for top tweets, what we also want to do is relevance, right? So we want to use different signals to figure out what tweets are actually good or got a lot of engagement. So we have some query-dependent scores, which is, for example, the Lucene text score. It always depends on the query you entered. Also, like the language, as you asked before, right? If you log in from the US, your profile is set to English. We want to rank English tweets higher than if I log in with the German account, for example. But we also have a lot of query-independent signals. For example, the text quality. If you write a tweet that has like 140 times the same character, it's probably not awesome text quality score. But we also have dynamic signals. For example, number of retweets, number of people who favorited a tweet or replied to a tweet, that kind of stuff. And of course, timeliness. We also want to boost a little bit higher. If two tweets have the same number of retweets, you probably want to show the more recent one first. So we have all these query independent signals here. So now if you think about the early bird that I described earlier, we have now a machine that has a lot of segments. Earlier I said 60 million. Actually, currently we run 8 million segments in production for different reasons. But it doesn't really change anything I described. So let's say we have a box that has a lot of those 8 million segments on disk. And now in all those tweets, we want to find the single best tweet for this query. So now we cannot early terminate anymore, right? Because you kind of have to search all to find the best one by definition. So but it would be really bad for every single query just to find one single tweet to search every single of those billions of tweets that we have. So so the idea is to introduce something, introduce a cache, a query cache, which is a yellow layer here. It's actually a cache for query results. So what it does is it maintains a bit set or a different data structure. You can configure that, but let's think about it as a bit set. It puts onto every segment a bit set of the same size, so 8 million, so it needs 1 megabyte of storage. And it marks the tweets that have a high query independent score. These are the red dots. Now, if you want to execute a query and find a top T for a user query, what we do is we say, okay, the user query, for example, is Lucene, and we rewrite that to the query Lucene, and we use the cache filter top tweets. And that filter basically is a Lucene constant score query that wraps a bit set. So what it basically does is it intersects the Lucene query with the red dots here in these yellow boxes. And it skips everything, because end queries are pretty efficient in Lucene. It skips on these posting lists always to those red dots, so it doesn't process the tweets in between the red dots, basically. So you only look at a much smaller amount of tweets than if we would not have the yellow boxes. And of course, we can control by setting a threshold how many red dots we want to have in the yellow box. So we can control the performance versus recall on top tweets by doing that. The query cache is nice. We can have multiple cache results, not only for top tweets. We could have other things we use that for. We can control in what data structure we use for the yellow boxes. So I talked about the bit set. We could also use a sorted VN list. It's basically just kind of an in-memory linked list, very similar to the early bird posting list format. But the sorted VN list is actually Lucene class. And we would use that if we have very, very few red dots here, where it wouldn't make sense to allocate a whole 1 megabyte bit set. We can configure an execution schedule and a cache mode and filter mode. So let's talk about that. So I talked about query independent signals, but that doesn't mean those signals are necessarily immutable. So when I tweet, 5 minutes later, maybe I have 10 retweets. And then I run the cached filter, and maybe that tweet doesn't make it into the yellow box because 10 retweets may not be enough. But then if I wait for a while, I could get more retweets. So maybe after an hour, it would make it into the yellow box. So we have to rerun that query periodically to make sure it's always up to date. So the execution schedule per filter determines how often I run the query, how often I rerun the query. And I can, with that execution schedule, I can also control, maybe on the most recent segment, I run it every 5 minutes. But on the older segments, I only run it once per day because, most likely tweets that are a week old or so don't get retweets anymore, or not so many. So there's no need to refresh it so often. You have different filter modes. And if you think again about, we read in this direction the posting list, and we append in that direction, right? So a situation that may happen is that we have a partially filled segment, the one that we are currently appending to here. So maybe it's a 1/4 to 25% fill up, and the next writer is currently appending to it. So at that point, we want to run that cached query that produces the yellow box. And then, as time goes by, the index writer keeps appending to the segment. But since we didn't rerun the cached query yet, the yellow box doesn't cover the entire range. That's why, as I had here on the previous slide, when we actually compute the yellow box, we remember the maximum doc ID to which we search to compute it. So now if we are in this situation, if we run the filter in cache-only mode, we only search basically the range that is covered by the yellow boxes. If we run in hybrid mode, what we do is actually we fall back. If we detect, oh, we have tweets that were appended since we last run the cached query, we execute the original query. We fall back to the original query for the most recent documents here. And then once we cross the max doc ID boundary, we actually switch over that to the bit set filtering mode. And this is actually how it looks, how you can configure that. So we can say, we define a filter called top tweets. This is a YAML file. We can configure a lot of different filters here. This is actually really how it looks like. We say, OK, we define a filter called top tweets. And what it actually the query it actually executes is the following query. It executes a score filter. It uses a scoring function called top tweets. And it only accepts documents that get a score between 0 and 0.21 and 1.0. So every tweet that gets a score using the top tweets function between those two values will become a red dot in the yellow box. And then you can say what the result type should be, bitset or the VN list, if you want to run in the hybrid mode or not. And here's the execution schedule. So for the latest segment, the youngest segment is segment 0. We do it every 5 minutes. For segments that are older than that, we only run it twice per day. Oh, that's it. So yeah, any questions about top tweets? The question was, do we have to mark in our engine tweets of spammers? Ideally, we wouldn't. Well, ideally, we wouldn't index them to begin with. We would detect it early enough. So we try that. But yeah, we also have ways to, like if accounts become restricted, for example, we have a way to not only mark tweets, but also users as restricted. And then we will never actually return results from those people. But that we really have to do for not only for the relevance mode, also for the real-time mode. So we do that as a post-filtering step. So even if you found the most recent 20 results, you go through a post-filtering step and toss those away that are from those antisocial users.
Thank you very much.